right? Okay, so we are recording the session, right? Okay, just move this. Okay, so hello, can you hear me?
Yes, Professor.
Okay, so what I want to mention, let me first talk about the topics of the exam. The topics of the exam will include the normal topics that we studied. Remember, until now, until the exam is the first chapter. Now, the first chapter means my lecture note, the first lecture note, where we studied electron as a particle, and when we applied F equal ma and classical physics, and we could calculate the conductivity of the particle, the conductivity of the material, the mobility of the electrons, the density of electrons, which is the number of free electrons per cubic meters or per volume. We also calculated the drift velocity of the electrons, and we said, in fact, we calculated the relationship between the drift velocity and the electric field, which is the mobility. And then we also talked about the current density, and the current density, which is the real Ohm's law, which is sigma E. Okay, so the sigma is the conductivity and E is the electric field applied to the material. For example, if I have a copper cable, for example, and this copper cable have a length L, and then there is a magnetic field, potential difference applied here, which will create an electric field. So this will make the electrons move with the drift velocity, and this drift velocity is proportional to the electric field by the mobility. Okay, and then we also mentioned the current density, and we also know that the current density is equal to the electric current divided by the area, the cross section. This is the area of the cross section, right? Then we also derived the equation of the current density, which is equal to the density of electrons times the electric charge and times the drift velocity. And then we got also the relationship between the density, conductivity, and the mobility. Okay, so this is basically what we have seen at the first part of the class. So, and as I mentioned, remember the electric field, in this case, for example, the electric field will be the potential difference divided by the length. So all these formulas, you will have to play with them depending on the situation. Okay. Then we went and talked about the Hall effect. Okay, the Hall effect. And the Hall effect is an effect that we see when we apply a magnetic field to a circuit. Now, this will create a polarization, and this we explained this in class. And then, depending on the material, we have the Hall constant, which is 1 over NE. So you can see that it depends on the material properties, because the density of electrons depends on the density of free electrons, depends on the material properties, of course. You can see it from here, that the density of electrons is related to J and is related to the drift velocity. Okay, and then we calculated the whole effect, the whole electric field due to this magnetic field, which is equal to the current density of the original circuit times the Rydberg, the Hall constant, and then the magnetic field applied. Okay, so again, as I mentioned, then you can play with these equations. I think the most important thing not the most important, one issue here is to know how to apply the magnetic field and how to do the whatever you want. Is it the right hand rule or whatever equation? Tool to understand in which direction the electrons are going. For example, if I have so let's say I have a potential difference here. Let's say we take the potential difference. This is a potential difference, to make it easier here. Let's do this. Let's write everything on the plane of this. Okay. So what will happen here? So we know in this situation that the electrons are going from which side to the other. So in which direction are the electrons going?
Positive to negative.
Yeah, but is it to the right or to the left?
To the
From
right.
left to right.
To the right. Positive
Yeah,
x-axis.
So the drift velocity will be this way, right?
Yes.
And the current will be the current and J, and the current density will be this one, right? This is negative, this is positive. Okay. Now let's assume I apply a magnetic field here. I apply a magnetic field to this circuit, and this magnetic field will go inside. Okay. So in which direction will the electrons go?
Doctor, I have a question. So the V opposite direction of I, right?
Yes, because the V is the drift velocity of electrons.
Is it always?
Yes, this is the drift velocity of electrons. So the drift velocity is the drift velocity of the electrons, the charge carrier. And the current, the electric current, is always in the opposite direction of the electrons. Okay. So now I apply a magnetic field which is going into the page. I have a drift velocity that is going to the right. In which direction the electrons are going?
Will it go up?
Okay. Okay. So I have yeah. So Hind and Yumna. Yeah. So you are right. Okay. So let me explain to you. I have the drift velocity here, right? And I have the magnetic field going inside. So the first thing is V cross B. V cross B or VD cross B will give me a vector that is going up. But the magnetic force is equal to QVB. And because the charge of the electrons is negative, then the electrons will move in this way. So the electrons will move this way. So there will be polarization here, and there will be positive charges here. Do you all understand? Okay. So this means that now I have an electric field that is a whole electric field, this EH. Okay. So now I have an induced electric field, right? And this electric field, let's assume that I have the distance D. Now the electric field will be equal to the potential difference here, which I will call VH, which is the potential difference due to this polarization divided by the distance d. Of course, this must be in volt and this must be in meters. Let me see if I have some questions on chat. Okay. Okay, so I have a question. So you want me to repeat the direction, right? This is what you wanted. So let me again take the direction. Now, again, as I mentioned, if you have any, so I will put it here. If I have a vector A, let's say a vector drift velocity or vector B, well, let's say drift velocity to just not to confuse you, drift velocity, and I have the magnetic field going inside. The VD, let me see, I will switch on my camera. Actually, I'm in the office. Can you see me?
Yes, Professor.
So now I will explain to you, because usually I explain it to you with the bottle, but let's explain it to the right-hand rule. What do I want to do? I want to do this VD cross B, because this is the force. The force is equal to Q VD cross B, right? So I will take the right-hand rule. This is my right hand. V cross B must give me the force, okay? So V is going to the right, right? V is going to the right, and B is going inside. So what happened? I have V cross B going up, but then I have a negative charge, so the force will go down. Is this clear? Okay, so with the bottle, I take the bottle, right? Okay, this is the bottle. Okay, so I have V and I have B going down inside the computer, inside the page. So I want to do V cross B, right? V cross B. If I want to do V cross B, I am opening the bottle. V cross B. I'm opening the bottle. So it is going up, but I have Q, which is the negative charge, so it's going down. Is it okay?
Yes.
Okay. If whoever did not understand, you can come on Sunday and I can explain it to you. Okay, so let's okay, so now let me switch the camera. Okay, so now, I mean, this is what I wanted to mention is just once you get the electric field, the whole electric field, then you have all the formulas here. You have the Rydberg, there was someone who told me Rydberg constant, and then since then I'm you know, it's wrong. It's not Rydberg constant. It's a Hall constant, Hall coefficient, and the electric Hall, and you have everything. Okay. Any question? Now the last part. Yes.
I have a question. We have the rule of NE is equals to JB over EH times E. Will it be given or we need to memorize this rule?
This one? This one?
No, it's NE equal JB over EH times E. JB over
Yeah.
E-
Where?
EH times E.
Times E.
Yeah.
Well, this is, you get it from where? Okay. Okay. So NE, what is, let's start from this one. Okay. What is AH is equal to what? Is equal to J. You know that RH is equal to NEE, right? B, right? Do you know this? Because
Yeah.
RH is this. So I just replaced RH. So NE becomes JB over AHE. So this, you can easily get it from here and from here. You don't have to memorize it. You have, if once you have this and this, you can get it, right? Did you understand?
Yes.
Okay, so in fact, yeah. So I have a question about this. I received a question about this. Well, actually, the electric field. This has nothing to do with the Hall effect. Whenever you have an electric field, this has nothing to do with this situation. If I have a positive potential here and the negative potential here, and this is a distance d, then there will be an electric field created by this, and the electric field will be equal to the potential difference here. So let's say delta V. So delta V divided by the distance. So this is everywhere. It has nothing to do with the Hall effect. Yes, we use it in the Hall effect, but this is a rule for the electric field. Whenever you have a potential difference, this potential difference will create an electric field, and this electric field, if it is uniform, which is the case here, is equal to the ratio between the potential difference divided by the distance, right? Okay, so let's move forward, because and then the third part, which is the part where we studied, is the wave propagation in solids. Okay, and the wave propagation, we obtained the dispersion equation, which is minus omega mu sigma minus I omega mu epsilon is equal to 0. So the wave propagation of solids tells me that the wave number is equal to real plus an imaginary part. Now, if we have seen that if it is a dielectric, then sigma is equal to 0, which means K becomes K real, and then there will be no attenuation. This we have seen in class, no attenuation. Okay, no attenuation, because if you look at the power which will be proportional to the magnitude of the potential. If you have the electric field, which is no, electric field, let's say EX, E0 exponential minus I, well, I omega t, I omega t plus or minus kx. Okay, and what happens here is the magnitude of x, which is equal to E0, to the square root, so E0 squared. And because here you have, so this is equal to E star E, the complex conjugate. And what happens is that because this is real, K is real in this case, so this one will be equal to minus IK real exponential IK real. Same thing for omega, because of the complex conjugate, and this will become 1. So there will be no loss. Okay, so this we have demonstrated in class. Let me see. Yeah. Okay. So now, and then of course, if sigma is large, then K is K imaginary, and then we have the thickness, the skin depth, and the skin depth is omega mu sigma, and you can see that the skin depth decreases when omega increases, which means like the material, the conductor becomes transparent to the wave. Okay. Yes, and then we have seen also that sigma omega is also equal to sigma 0, which is sigma at the DC 1 minus I tau omega, and tau is the collision time, okay, or the relaxation time. So now let's go and start some problems, because I need to start some problems. So here is a problem. Can you see the, or I should increase a little bit? Okay.
Before starting this question, can I ask you how can I find the rule of V whole?
No, the V whole, well, there is no rule. Either I will tell you, I will give you the whole voltage, potential difference, or I will ask you to find it. Okay, it just so the voltage, the whole voltage will be, as I mentioned, in the case that we did, we have the potential difference going, the electric field going this way. Sorry, the drift velocity going this way of the electrons, because I have this. Okay, and then what happens, as we mentioned, what happens is because the magnetic field is this way, the electrons will be this, and the positive charges will be here, and here it will be VH. Okay, so depending on the situation, either you will be given like this one. I think yes, this one is yeah, we give you the potential difference, for example, in this example. Yeah, you can see a magnetic field gives an output voltage of 10.45 millivolt. So let's do this problem. Okay. So a Hall effect element used for measuring a magnetic field strength gives an output voltage of 10.5 millivolt. So this means that VH is equal to 10.5 10 to the negative 3 volt, right?
Yes.
Okay, so let me see. The element is made of silicon and it is 2.5 millimeter thick. Okay, so here we are already given the distance, the thickness. Okay, so we are given the thickness. The thickness is 2.5 10 to the negative 3 meters, and produce a 4 amps. So it carries an electric field. Sorry, it carries a current. So I is equal 4 amps. The Hall coefficient, so we are given also the Hall coefficients. What is the value of B? Okay, what is the value of B? Now, let's look at the formulas that we have. The formulas we have is the Hall effect, the Hall electric field, is equal to the potential difference divided by the distance. We have this, we have this. And what do we want? We want the value of B. Well, the value of B, we know that, for example, that the whole electric field is equal to J RH B. Are you following?
Yes, doctor.
This is given. This is, we can calculate.
So we
I don't know
try to
this,
find J.
and I don't know this. So we need to find J. Well, we know that J is equal to the current.
I over A.
Yeah, the current divided by A. And A is, it is, the thickness is 2.5 millimeters. Now you have two choices here. So those who would consider thickness of a square, it's okay, or a circle, it's okay, it's not a problem. So here you have 4 amperes divided by the area is 2.5 10 to the 5, and then you have to convert it to millimeters, which will be to meters, which will be 10 to the minus 3, 10 to the minus 3, which is 10 to the minus 6. Okay, so this is J. All right, because I converted 2.5 to millimeters, which is 10 to the minus 3, and 2.5 to millimeters, which is 10 to the minus 3. This gives me an area, and then the B becomes EH, which I already find here. So what is EH? EH is equal to 10.5 divided by 2.5. I'm not converting because both of them are in milli, so it is straightforward. Okay, and I think it gives me 4.2 volt per meters, and J it's 64.640123 amperes per square meters, and then B will be just the rest, so will be 4.2, which is EH, divided by 64123 times RH, and RH is given, which is 4.10 to the negative 6. Okay, so I think this will give you 6 Tesla. Okay, any question?
Why is the area? Why is that 2.5 times 2.5?
Because I just took the area as a square. Okay, it's like if I have this. This is the element that I have, right? And this is thickness. Okay.
Professor, we always assume that it's going to be a square.
Okay, so as I mentioned, if you consider that it is a circle and you do pi r squared,
that's
fine, no problem. Okay.
Both are correct, both assumptions?
Yes, unless I give you. In this,
it
was not clear, but unless I give you that, no. Like the one that I gave in the sample exam, no, I gave a square, not a square, but a rectangle. So you have to find the. If you remember, there was one problem where we did this, right? Okay. Okay. And we said, well, the current is going this way, whatever. Then this will be the area. And then you have to, let's say, if I have this is B and this is D, then the area will be D times B, right?
Yeah.
Okay. Okay, so let's go to the second part. Again. So here, I think this was a question of the quiz. By the way, I'm doing the quiz, and then I will do quickly the 2 first questions of the exam of I think 2021, something like that. This was a question of the quiz, and many students were asking, and we need material properties, etc. What is the question here? Question is, what is the ratio? Read the question, please. I'm asking about the ratio. I'm not asking you to compute the skin depth for each one of them. No, I'm asking about the ratio. So the ratio of an electromagnetic wave inside the conductor, so the ratio of the skin depth inside the conductor for corresponding frequencies at 10 and 25 gigahertz, assuming the same material properties. So this is a very easy question. So delta that corresponds to 16 hertz, I will call it delta 16, is equal to 2 divided by omega 16. Omega 16 means omega that has 16 gigahertz. And then the same properties of material. And delta 25 is omega 25 mu sigma. Well, I'm talking about the ratio 16 divided by delta 25, it will give me, it will give 2 over omega 16 mu sigma times omega 25 mu sigma divided by 2, because remember, we have to flip. And then mu is the same property, so at the end it becomes omega 25 over omega 16. So what is this? Well, what is omega? Omega is 2 pi f frequency. So 2 pi 25 gigahertz 10 to the 9 divided by 2 pi 16 10 to the negative 9. Okay, here. So at the end you have 25 over 16. Sorry?
No, I was calculating.
And then I think 1.1.
Also, I have a, so why isn't it, so at first we said the skin depth of 16 over skin depth of 25. Why is it like the opposite? Why would you assume this is the case?
Well, you, usually when you have a ratio of 2, when you are asked to calculate the ratio of A and B, so usually A over B. Now, if you do B over A, it's okay. I mean, you will get 1 over 125, so it's not a problem. The real problem is that some of you started asking about sigma and mu, and we don't have sigma and mu. But I'm not asking sigma and mu. I'm asking about the ratio. So whether you do A over B or B over A, it's okay. It's not a problem. What is important here? Which skin depth is bigger, the 16 or the 25?
16.
16. Okay, because the higher the frequency, the higher the attenuation. Okay. Yeah. Okay.
We have to
Professor,
write it.
in other words, the skin depth 1 is greater than skin depth 2 by 1.25, yes?
Exactly. Yeah. So you lose 25% more with 25 gigahertz.
Okay, so do we have to write it or no?
No, I did not. Here, I did not ask you, but I might ask you. I might ask you what is the conclusion? Which one we will lose more? Okay. Again, this question is sometimes just because you don't really read the question, and it created confusion, right? So what is this? It is fine if we divide 25 by 16. It's not a problem. It's not a problem. Yeah. You will just get 1 over 1.25. Okay, so calculate the value of KT. Some students, I honestly, I saw some students struggling a lot with this problem. And in fact, because you did not read the question, the value of K times T, K is the Boltzmann constant, and T is the temperature. So here I'm just asking K times T, which is equal to in electron volt, because this is energy. Remember that KT is the energy, is a unit, its unit is energy. So what is K? K is given in joule. So KT, the dimension, is given in joule per Kelvin, at least what is given here, times the temperature in Kelvin. So the final result will be joule. So you have just to convert joule to Kelvin. So you have several ways. Either you do 1.38 10 to the negative 23 times 300, and then you divide by 1.6 10 to the negative 19, and this will give you electron. Okay, any question? Okay, so the conclusion that okay, one student, that's why if you, yeah, okay, one student, so we did the skin depth of, sorry, I have a question about the problem, the previous problem. delta 25. I found 1.25. Okay. Well, what is the meaning of that? The meaning that the skin depth of 16 gigahertz is bigger 25% than the skin depth of 25 gigahertz. Okay. This means that what is the skin depth? The skin depth is the thickness at which 63% of the signal will be attenuated. Now, this means that the 25 gigahertz will be attenuated at a shorter distance than 16 gigahertz. Okay. Okay. Okay, here I have one remark here. I will give it to you, but regardless of the result, what is the conductivity of the whole when the Hall effect is 5 and 5 and the mobility is 5? Okay. Here there was, in fact, there was a. I will first. How do you solve this problem? So we need the conductivity. So we need sigma. Okay. And we know RH.
And the mobility.
And we know the mobility. Well, we know that sigma is equal to NE from E times E mu, right? And we know that RH is equal to NEE, right? So this means that sigma is equal to mu over
NE over NH, yeah.
Right? So that's it. Now, just to be frank with you, there was a mistake here. In fact, this question, I did not realize that I put it as, I did not even give the unit, but those who did in the quiz 5 divided by 5, it's 1, it's okay. It's not a problem. But yes, there was just a typo here on the question, but it's not a problem. Any question?
Professor, don't we have to change 5 centimeters squared to meter squared?
Okay, so if I give you, and this is I explained in class, if I give you the easiest way, if the Hall effect is given in centimeter cubed, and for example the mobility is given in centimeter squared, the result, the sigma, will be 1 over omega centimeter. Okay. So you know that this is centimeters, so this will be centimeters. Okay.
Okay, Professor, thank you.
Okay. Okay. Again, this is a question. This is the exam. This is the exam that I did not post it, I think. But yeah, because I can post it, but it's so a free electron. A free electron. I'm reading the chat questions. Free electron in a material has a thermal energy at 3 Kelvin. Its mass is 20 times the less than mass of a normal electron. Calculate the thermal velocity. Okay, what is the thermal velocity?
VTH, yes?
Okay,
VTH.
so 1/2.
Half mv/t squared equals 3 by 2 kT.
3 over 2.
Yeah.
Boltzmann constant time temperature in Kelvin. No, Boltzmann's constant. Okay.
Who is speaking?
Jakob.
I recognize. Okay, so how do you solve this?
We
Well,
multiply
K is
2.
given, huh?
Multiply 2, so 2 is gone, and then we move the M to the other side.
Now the only thing here is the mass. The effective mass here is the 20 times less the mass of a normal electron. So it will be ME, the mass of the electron divided by 20. And that's it. So you have the Boltzmann constant. The Boltzmann constant will be given, which will be in joule per Kelvin. The temperature is 300 and the mass is given. So that's the question.
I mean, just 9.1 to the times, right?
Yeah, the mass will be given, yeah, 9.1, 10 to the negative 31 kilogram. But the mass of the electron will be given. No, the mass is always, we are talking about SI unit. SI unit, we learned them in the first year of engineering. So the mass must be in kilogram, time must be in second, length must be in meters. Okay. And of course, the magnetic field must be in Tesla because we don't use other units of the magnetic field like Gauss, etc. So we use those. Those are the SI unit. Okay, let's go to the second question. So the second question, an experimental measurement reveals the following data about a material X. So the resistivity is given. So we are given the resistivity, we are given RH, and we are given atomic mass. Okay. Well, actually, the reason I'm giving the atomic mass, I think, because we will be giving it, using it later. Okay, don't worry. So the question is, calculate the density of electrons. What is the density of electrons?
NE.
So we want to calculate N. So how do we do?
RH equal 1 over NE multiply E.
Exactly. And RH is given. So NE will be equal to 1 over RH E, which is 1 over 2.5 10 to the negative 10 times E, which is 10 to the negative 90. Okay, so it will be, I think, let me see, yeah, I have it, per cubic meter, right? And then, see, this is A, this is B, calculate the mobility. How do you calculate the mobility?
The conductivity is equal to MNE multiplied by E.
Exactly. I want to see who is speaking. So you said this, right?
Yes.
Okay. And then mu is equal to
And we can get the resistivity from the conductivity. It's 1 over 4.7 times 10 to the power minus 8.
Yeah. So this will be equal to NE, E, and the resistivity, right? Right? And then you have everything. You have the resistivity, and the resistivity is in meters, and the Hall coefficient and the NE is cubic meters. So you will have everything, right? Now the collision time. So collision time is tau. How can you compute the collision time?
Is it mu is equal something multiplies by tau over m?
Yeah, E over m divided by, yeah, E tau over m, sorry. Yeah, E tau over m. Mu is equal to E tau over m, which means tau is equal mu m over E. Now, if I didn't give you the effective mass of the electron here, then you just use the mass of the electron. So it's mu that we calculated here, and then 1.6 10 to the negative 19, and then, no, sorry, no, this is the mass of the electron. The mass of the electron is 9.11 10 to the negative 31, and then 1.6 10 to the negative 19, and then you get the time in second. Any question?
So we don't use the atomic mass, which is in the question, right?
Sorry?
We don't use the atomic mass, which is in the question.
No. I think in this exam, there was a fourth question that we used, yeah, yes. Yeah. Okay. Then let's go to the other part, which is this one. Okay. Okay. We propose to study the propagation of electromagnetic waves through the material X given above. Okay, so now we have a material that the same material as above. Remember, for this material, we found the mobility, we found we have the conductivity, and what did we found? We found also the electron density, etc. So the first question is, using the dispersion equation and the expression of the AC conductivity, prove that the wave number K of the wave can be written as. Well, these kind of questions prove, and I'm already giving you the solution. I think it's very easy. So what you would do, the first thing is the dispersion equation. The dispersion equation is minus omega. Yeah, so the dispersion equation is minus omega mu sigma minus I omega mu epsilon is equal to 0. And I want, so well, I can do, it is equal to I omega mu sigma minus I omega mu epsilon. And I want to write this as a function of this. Well, the first thing, let's develop. So K squared is equal to I omega mu sigma. I times I is -1, so it will be plus omega squared, right? Mu epsilon, right? I did not, yeah, okay. Okay, now I know that sigma omega is equal to sigma 0 divided by 1 minus I tau omega, right? Then I replace, so K squared becomes, I will, what I can do, yes, so it's omega squared mu epsilon plus I omega mu, and then sigma. Sigma is sigma 0 over 1 minus I tau omega, right? Are you following? So K squared is equal, what I will do, I will put this in common. So it's omega squared mu epsilon, and then it's 1 plus I omega mu sigma 0 over omega squared mu epsilon 1 minus tau omega. Right? Are you following?
Yes, Professor.
I can get rid of this.
Professor?
Yeah.
Can you repeat the step where how we got 1 plus I omega mu, like the right side of the equation?
So what I did, I put this in common. So if I put this in common, I will get 1 here, and I divided by this, by the same quantity here. So it's like when you put it in same denominator, right? Do you see it?
We took common factor for the equation.
So, wait. You are asking me about this, right? How did I go from here to here?
Yes.
So I have omega square mu epsilon plus this. So what I did, I put omega square mu epsilon in common. From here, it will give me 1, right? Do you agree?
Yes.
Yeah.
And from here, well, because I put it in common, I need to divide by it, by the same quantity, right? It's
Yes.
like if I have, let's say, if I have Z is equal A plus IB, and I want to put A in common. So it will be A 1 plus IB over A, right?
Yeah.
Okay.
Yes.
So K squared becomes omega squared mu epsilon 1 plus I sigma 0 over omega epsilon 1 minus I tau omega. This is the question. And then if I put, now I can do K square, the square root of K square. So K becomes the square root of this, which is omega square root mu epsilon, and then all of this square root. This is exactly what I wanted to prove. Okay, so this is what I wanted to prove. Remember, you have a half here, 1/2. So this is exactly what I have to do. Now, I have a question. What is the unit of this? Who can tell me give me the unit of this? Let me look at the answers. Okay. Yeah, I have one good answer. Who can?
Mu is no permittivity is Farad per meter or
Yeah, Farad per meter and Henry per meter. But we okay. Okay, no, in fact it's the opposite. It's some of you said this is the unit of a speed. No, in fact it's the unit of 1 over the speed, because remember the speed of the wave is equal to 1 over mu epsilon, right? Okay. Okay, we did it in class, by the way. So please remember this. So we obtained what we were looking for, which means 1 plus I sigma 0 over omega epsilon 1 minus I tau omega. Okay. So this is the question where mu, epsilon, tau, and sigma zeros are respectively the permeability, permittivity, collision time, and DC conductivity of the material. Okay, so this is what we now prove that the same wave number can be written as this. All what you have to do, so we need to prove the following to prove that K is equal to omega mu epsilon. All right, this is already given. That can be written as A plus IB 1/2. Okay. Now, what do I have to do? I need to take this and to write it as A plus IB. So I need to take this 1 plus I sigma 0 over omega epsilon 1 minus I tau omega. I need to write it as a real number and imaginary number. Okay. So how do I do this? Well, the only thing that I can do is to multiply by the complex conjugate of this guy here and here. So this will give me 1 plus I sigma 0, 1 plus I tau omega. Remember, I is multiplication of everywhere. And then omega epsilon. So A plus IB times A minus IB, the complex conjugate, gives me A squared plus B squared. This you know. So this means that if I multiply by here and I multiply by here, it will be 1 plus tau omega squared, right? And then I distribute. This will give me 1 I sigma 0 minus tau omega sigma 0 divided by omega epsilon 1 plus tau omega squared, which is equal to 1 minus tau omega sigma 0 over omega epsilon 1 plus tau omega squared plus I sigma 0. All what I did, I distributed 1 plus tau omega squared. So this is A, and this is
B.
Yeah. So very okay, right? Any question? Any question? And then I did not copy but then because now I have K, it will be like an A plus IB. So this means that K will have an imaginary, a real part. This is a real part, and this is an imaginary part. And then what I asked you is to calculate, or ask the students to calculate the values of A and B for the electromagnetic waves 7 and 10 to the 15. Why I did this? To show them that when the density, okay, so let me do the following. A, as you can see, A depends on omega, etc. I have a question here, a qualitative question. You don't need to calculate. For 10 to the 5 hertz and 10 to the 17 hertz, which one will be bigger here? Which one will become, let's say, if I calculate, this is A1, B1, and this is A2, B2. Which one is bigger? Is it A1 or A2?
A1.
So A1 is bigger. And which one is bigger, B1 or B2?
B2.
B2. So what happens is, in fact, what happens is at low frequency, the imaginary part is smaller because the imaginary part of the wave number is the one that is responsible for the attenuation, remember. Okay, when you go for larger frequency, the imaginary part becomes bigger and the attenuation becomes bigger. That's the real question, the real goal behind this question. Okay, so I am done with the review session. All what I can tell you that those are the 3 concepts that we mentioned for the exam. The first part is how to play with the values. Let me go back to the first part. The first part is how to play with those values. Sigma, mobility, conductivity, electric density, the current density, etc. Because you really, as electrical engineer, you need to master this. Okay, this is pure electrical engineering for conductors. Okay, we will see them also for semiconductors. We will also calculate the conductivity for semiconductor, for holes, and so this you need to know throughout the whole course. And then what happens to the Hall effect when what happens to those to a conductor or a semiconductor when the Hall effect, when we put the circuit into a magnetic field. Remember, the Hall effect means that we have an electric field, an induced electric field. The induced electric field must be bigger if we want to notice, to measure it. We should have enough magnitude for the whole electric field. A whole electric field means higher electric field means higher Hall constant. But the problem, the Hall constant is inversely proportional to the number of free electrons, which means for the metals, it's hard for the metals, because the metals has a higher number of free electrons. It is hard to notice or to detect the Hall effect. We are talking about microvolt. And that's why most of the time we use semiconductors. Remember this. For the Hall effect, most of the application of the Hall effect, we use the semiconductors. Okay? And then you need to know the dispersion equation and how the dispersion equation gives us the attenuation of the waves in the solid as a function of the wave properties and also the metal properties. The metal properties means sigma, okay, the conductivity, and the wave properties means the frequency. Okay, we have more attenuation when we have a higher frequency and when we have higher conductivity. Okay, and then the skin depth. That is really the goal of this exam and of this course. Okay, so I will stop here. You can ask me questions, but I still have, I'm in the office. I have to go home.
I would just want to check what are the equations that will be given? Like, is it the same as the quiz one, or
the same as the quiz? Maybe there is one or two that I did not put in the quiz, but yeah, those are the equations that you will need. You don't, I mean, if you need the mass of the electron will be given, the charge of the electron, the Boltzmann constant will be given. So you don't really need anything except you have to exercise yourself how to play with these equations. Okay, so yeah, so I will stop here. I will post this video and I will also post those notes. Okay.
Thank you, Professor.
okay, is VH gonna also come, or we have to memorize it?
Sorry, the
VH.
VH.
Yeah, we can like play with it and deduce it, right?
No, look, as I mentioned, honestly, I don't know what is the problem with VH. VH is a potential difference. It's a potential difference. Okay, so VH is a potential difference. For example, if I tell you I have a potential difference of 0.1 millivolt and the thickness is 1 millimeter. So what is the Hall effect? The whole electric field? Well, it's 0.1.
0.1 over 1.
Yeah. So, so I really don't know what is the problem with VH. VH is a potential difference. Either I will ask you to calculate it. For example, I will give you, okay, we have seen 1 volt per meter as electric field in a distance of 1 millimeters. What will be the potential difference that we would measure, or something like that, right? So it's really not a problem. Okay. So have a good night and a good weekend, and see you inshallah at 5 on I will try to be 15 minutes before. Yes, Fatma. Yes, please go ahead.
Professor, I just have a question for the exercises you gave us. It was 8 questions. They're all included, right?
Yes.
Okay, thank
Yeah,
you.
but honestly, what I did, I selected the most important ones. Yeah.
Okay, Professor, can also you'll upload this video, right? Like,
Inshallah.
okay, thank you,
So
Professor.
you are
See you.
giving me more work.
No problem.
By the way, I see some students from the other sections, right? Right? Well, you are welcome. I think they have also an exam, right? They have also an exam. So if you have any question, just come to my yeah. So okay, Fatma and Nama. Yes, some of the questions. There was one question about VH, yes, in the quiz. For those who yes, the answer was none of the above. Yes, Fatma, you are right. Well, for example, let me tell you, I will give you, for example, let's assume that you know that the mobility is equal to mu tau over m, right? I will give you, not in the quiz, for example, this is what I gave, for example. So what is the definition or the formula of the mobility? Does it depend on 1 over time? Does it depend on 1 over magnetic field, or does it depend on 1 over whatever electric field, right? So it could be none of them. It was just a question with whatever formulas, just to show, and then none of the above. For example, none of the above. Yes, the answer was none of the above. Okay. Okay, see you on Sunday. Have a good day. Bye-bye. Install. Yeah.